Every year, 2.6 billion tons of carbon dioxide are emitted in the atmosphere in the production of steel. And for the concrete industry, this number is 4 billion tons of carbon dioxide. These two industries make up a significant portion of the world's carbon dioxide emissions, and as such, researchers have been looking for ways to reduce this number. And due to the prevalence of these two materials in construction, people have been looking for alternative materials to use instead of concrete and steel. One of these is wood. But despite its low cost and abundance, its strength pales in comparison to steel and concrete. So I guess that's the end of that. Wait, what's that? It's a bird. It's a plane. No, it's... superwood! So you may be super confused about superwood. What is it? It's a stronger, densified form of wood made by first removing some of its components and then compressing it. So wood is made of three main components: cellulose, hemicellulose, and lignin, with this hemicellulose and lignin being the two main components responsible for keeping the wood rigid and firm. And to compress the wood, we first need to remove these two components in a process known as delignification, where we boil the wood in a special solution for a few hours, causing the hemicellulose and lignin to break down inside the wood. The end result is a wood that's soft, scriptural, and perfect for compression. Afterwards, the wood is sent to a hot press, where it's boiled at 100 degrees Celsius for 24 hours. In this process, the heat and pressure causes the cell walls inside the wood to break down, and for the cellulose to get close enough to form hydrogen bonds, resulting in the increase in strength exhibited in superwood. Now, this sounds good and all, but a major drawback of superwood is that as thickness increases, the efficiency of our delignification process decreases. And this is important, as in order to make superwood viable for the construction industry, we first need to increase its strength beyond what has been seen in testing. And this problem cannot be solved just by boiling the wood for longer, as boiling the wood for too long would cause the degradation of cellulose, resulting in less cellulose in the superwood and fewer hydrogen bonds, resulting in an overall weaker superwood. This is why my lab set out to test the effects of changing thickness had on superwood. And to do this, we ran chemical composition tests and strength testing. The first test we did to test the chemical composition of the wood is FTIR testing, Fourier transform infrared spectroscopy, the results of which produces a graph with an intensity for each wave number in the wood sample. Some of these wave numbers, as seen by the dotted lines in the chart, correspond to bonding inside some of the components of the superwood. So for example, at the dotted line at 1730, this corresponds to the bonding in hemicellulose. For the green line, representing the raw sample, you can see that there's a dip. And this dip shows that there is hemicellulose inside this wood sample. However, if we go to the black line, the 12.5 millimeter sample, you can see that this dip has mostly flattened out, showing that the delignification process has in fact removed the hemicellulose from that sample. Other trends we found were that as thickness increased, for our thicker samples, the decrease in hemicellulose and lignin is less significant. However, you can still see a decrease, which shows that our delignification process has in fact removed lots of the hemicellulose and lignin. The next test we ran is X-ray diffraction testing, the results of which produces a crystalline index. Now, the reason this test works is due to the crystalline structure of cellulose, and the hemicellulose and lignin are not crystalline. Oh wait, my mouth's kind of dry. I'm gonna get some water. That water's been sitting out for like an hour. It's pretty warm. You know what it could use? Some ice. Wait, ice. You know something about ice? Ice has a crystalline structure, just like the cellulose. The cellulose molecules, it forms a pattern just like this, allowing it to be used for X-ray diffraction testing. To the right, we have a chart showing the crystalline indices for each of our wood samples. The highest crystalline index we received was a 63% crystalline index for our 12.5 millimeter sample. And of our treated samples, the lowest crystalline index we got was 55% from the 37.5 millimeter sample. While this may not be as large as our thinnest sample, this is still a 15% larger crystalline index over our raw wood sample of 40%, showing that our delignification process has, in fact, removed hemicellulose and lignin from the wood. Now, this is good, but now we need to put this superwood in action. To do this, we tested the strength using a 3-point bending strength test, where the beam of wood is placed on 2 supports, the two of the points, and a third point is where a load is applied to the center of the wood, causing the wood to bend and ultimately break. And here are the results. Our highest performing sample was the 12.5 millimeter sample, showing a 50% increase in strength over our raw wood. And while not as good, our 25 millimeter sample showed a 20% increase in strength over the raw wood. However, something my lab was not expecting was the 20% decrease in strength exhibited by our 37.5 millimeter sample. However, we suspect that this could be due to natural cracks and fissures inside the wood that would just result in a bad sample. So from these results, we can conclude that even as stimulation increases, our superwood treatment is still able to have an effect. So this opens the way for further testing by labs, and thus we may be able to see superwood in construction industries in the future. Now, an important part of the scientific process is background research, and I had to do this so I could even find out what superwood was. However, a common problem I came across is the locking of scientific articles behind paywalls. I looked this up, and this isn't just a struggle that was unique to me, and that many others had this problem as well. Additionally, I found a movement, Open Science, which aims to open up access to scientific articles to everyone. This improves the spread of knowledge inside the scientific community, and allows others to build upon each other's work more quickly. As well, another goal of Open Science is to open up scientific articles to not just researchers, but to the general public as well, similar to this launch presentation. So why should you care? Open Science, it shows the collaborative spirit of research and how we can all build upon each other, how researchers can build across each other's work, connecting researchers across continents, across bodies of water. Superwood is no exception. It was not actually developed at LSU, instead being developed at University of Maryland. And our lab at LSU focused on optimizing the superwood, showing out how we can build upon each other's work. While superwood may just be a construction material, it can be so much more to us. Be strong, be supportive, be revolutionary, be like superwood.